In this lesson, we are going to discuss a method used to approximate functions using polynomials. These approximating polynomials are called Taylor polynomials. So first, let's start by finding a first-degree polynomial function whose value and slope agree with the value and slope of the function sin x at x equals 0. Now this is a fancy way of just saying that we can find the tangent line, because the tangent line passes through the graph at that point, and it has the same slope. So remember, to find the tangent line, you have to use the derivative. So the derivative of sine is cosine, and when you plug in 0, that gives you the slope of your tangent line, and cosine of 0 is 1. Now, at x equals 0, that's the x-coordinate. At that point, the y-coordinate is also 0. So the equation of our line is y minus 0 equals 1 times x minus 0, or y equals x. And that's sometimes called P1 of x, the one meaning it is a first-degree polynomial approximation. And actually, if you're near 0, sine of x is very close to this function. So here's a graph of sine. There is the line y equals x. And as long as you're close to 0, the tangent line and the function aren't very far apart, and you can find values of sine of x by plugging x instead into this polynomial function. Now, how might we make this estimate better? Because obviously that line is straight and the sine function is kind of curvy. So what we're going to do is we're going to look for an nth degree polynomial, p sub n of x, equal to some a0 plus some a1x plus a2x squared plus a3x cubed up to some a(n)x to the nth power. And what we're going to require is that the polynomial's value at 0 equals f's value at 0. And we're going to require that the polynomial's derivative of the polynomial at 0 be equal to f prime of 0. And that the second derivative of the polynomial at 0 equals the second derivative of f at 0, etc. So the third derivative of the polynomial should equal the third derivative of the function, etc. And our question we need to figure out is, how are these coefficients, the a0, a1, a2, a3, how are those related to the original function itself? So to investigate that, because the relationship is defined in terms of derivatives, we have to find some derivatives. So the derivative of this nth degree polynomial is going to be, so a0 is a constant, its derivative is 0. a1x's derivative is a1. The derivative of a2x squared is 2a2x plus 3a3x squared plus etc. And the last term's derivative will be n a sub n x to the n minus first power. Let's repeat that process a couple times. The next derivative will equal a1's derivative is 0. The derivative of 2a2x will be 2a2 plus 3 times 2a3x plus etc. The last term will be n times n minus 1 a sub n x to the power of now n minus 2. And we'll just do one more. The third derivative will be 3 times 2a3 plus up to n minus 1 times n minus 2 a sub n x to the power of n minus 3. Now let's go back to these requirements here. So the requirement that p sub n of 0 equals f of 0, that implies that when you plug 0 into the original function, into this p sub n function, so when you plug 0 into that function, every term is 0 except for that a0. So a0 will have to equal f of 0. So my first term is equal to the function's value at 0. Now, next we have that Pn prime of 0 has to equal f prime of 0. So look at the equation for p prime. When you plug 0 into that, you get a1 has to equal f prime of 0. So the next coefficient is equal to the derivative of the function at 0. Now next, the second derivative has to equal the second derivative of f, and that will imply, so looking at the third equation we have there now, so plugging 0 into the polynomial's second derivative, we have 2a2 is equal to f prime prime of 0, or solving for a2, we see that a2 is equal to f prime prime of 0 over 2. And if we do one more, you'll see the pattern. So finally, the third derivative at 0 has to match the function's third derivative at 0. So that gives us that this 2 times 3, a3 must equal f prime 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 of 0, or a3 is actually equal to the third derivative at 0 over 3 factorial. Remember, 3 factorial is 3 times 2 times 1. This 2 times 3, adding in the multiplication by 1 won't change it. So that's what the third coefficient is. And in general, a sub n, so the nth coefficient, will be equal to the nth derivative of your function f at 0 divided by n factorial. So that's the general formula for those coefficients. So using that information, we have that this approximating polynomial, Pn of x, is given by f of 0 plus f prime of 0 times x plus f prime prime of 0 over 2 factorial times x squared. 2 factorial is just 2, plus f triple prime of 0 over 3 factorial, x to the third, up to whatever n you want to stop at, the nth derivative at 0 over n factorial times x to the n. That is something called the Maclaurin polynomial, because it's at 0 specifically. Now, let's do an example where we just sort of discuss how accurate these things are, at least comparing an approximation to an actual function's values. So, first of all, let's just verify. We're going to compare this third degree polynomial with sine x for several values of x near 0. But first, let's talk about where that came from. So p3 of x, as we just discussed, will equal f of 0 plus f prime of 0 times x plus f prime prime of 0 over 2 factorial times x squared plus the third derivative at 0 over 3 factorial times x cubed. Now, the function we have is sine. We need to find the first 3 derivatives. So f of x is equal to sine x. F prime of x is equal to cosine x. F prime prime of x is equal to negative sine. And the third derivative is equal to negative cosine. And then, using our formula, the third degree Maclaurin polynomial is equal to sine of 0 plus cosine of 0 times x minus sine of 0 over 2 factorial times x squared plus negative cosine of 0 over 3 factorial times x cubed, which, if you remember that sine of 0 is 0, gives us p3 of x is equal to x minus x cubed over 3 factorial. So that's where that comes from. Interesting thing, sine is an odd function. The degrees, or the powers on the terms in this polynomial, are also both odd. Alright, now let's make that table and compare the values of this function to the values of sine. So sine x and then p3 of x. And this estimation is constructed around 0, so it is accurate near 0. It's obviously not going to be accurate if x is equal to like 125. But for things close to 0, it is pretty accurate. So if you input, say, negative 0.5, negative 1/2, into the sine function, you get an estimate of negative 0.4794. Make sure your calculator is in radians, not degrees. When you plug negative 0.5 into this p3 of x, you get negative 0.4792. So the only difference there is in the last digit. When you plug in something like negative 1/10, you actually get that the 0.0998 when plugging into sine, and you get 0.0998 when plugging into p3 also. So those two values are different if you look at decimals further along, but for the first 4 digits at least they agree. When you plug in 0, both of these functions agree and they're both 0. And because of the oddness of sine, plugging in 0.1 gives us 0.0998, and the polynomial is also odd. So indistinguishable nearly, at least to 4 places of accuracy at 0.1, and at 0.5 we have 3 places of agreement. So 0.4794 and 0.4792. Now the method discussed in the previous example works when you are approximating a function near 0, but you might want to approximate a function near some other value. Say you want to find sine of 125 and you need to do an approximation, and centering your approximation at 0 would require that you use a lot of terms to achieve that accuracy. But instead you could just choose to sort of start your approximation at the value you cared about. So that is what's called a Taylor polynomial. So we'll talk about where this comes from, but you can see that the form is pretty similar to what we did in an earlier example. And this equation there, that's what we derived early on. So this is called the Maclaurin polynomial, and Maclaurin means that your value of c is equal to 0. Let's discuss where the Taylor polynomial comes from, having centered at c. So we'll start the same way. We have a polynomial function, and it's equal to, so Pn of x is equal to sum a0 plus a1 times x minus c plus a2 times x minus c squared plus a3 x minus c cubed plus an x minus c to the power of n. And find repeated derivatives. So the first derivative will just be a1. So a naught's derivative is 0. If you distribute that a1, we'll have a1x minus a1c, and a1c's derivative is 0, plus 2a2 x minus c plus 3a sub 3 x minus c squared plus n a sub n x minus c to the n. Should be pretty familiar. The next derivative, so the second derivative of p sub n, will be 2a2 plus 3 times 2a3 times x minus c plus n times n minus 1 a sub n x minus c to the n minus 2 power. And the third derivative will be 3 times 2a3 plus all the way up to n minus 1, n minus 2, a sub n, multiplied by x minus c to the n minus third power. So, etc. Now, at the point x equals c, we want p sub n of c to equal f of c. And so what that implies when you plug c into your polynomial, so what happens then is every term is 0 except for the a sub 0. So we'll have a sub 0 equals f of c. In the previous time we ran through this sort of process, we had a sub 0 equal to f of 0 because our c value was 0. And then next you want the derivative at c to equal the derivative of f at c. And that will imply, looking at this second equation, that a1 is equal to f prime of c, just like before. Now the second derivative of the polynomial at c needs to equal the second derivative of the function at c. So that tells us that 2a2 has to equal f prime prime of c, or, once again, a2 is equal to f prime prime of c over 2. And finally, just one more, the third derivative at c has to equal the third derivative of the function at c, which tells us that 2 times 3, or really 3 factorial a3, has to equal the third derivative of the function at c, or a3 will equal the third derivative at c divided by 3 factorial. So just like before, in general, the nth coefficient is equal to the nth derivative at a value c divided by n factorial. And that is where that Taylor polynomial equation comes from. Now let's find the nth Maclaurin polynomial f of x equals e to the x. So the Maclaurin polynomial in general, Pn of x, is equal to f of 0 plus f prime of 0 times x plus f prime prime of 0 over 2 factorial times x squared plus the third derivative at 0 over 3 factorial x to the third up to the nth derivative at 0 over n factorial x to the n. Now, e to the x is a nice simple function. The derivative of e to the x is e to the x, so the second derivative of e to the x is e to the x, all the derivatives are e to the x. So that tells us that because f prime of x is equal to e to the x, f prime prime is equal to e to the x, f of 0, f prime of 0, f prime prime of 0, all of those values are equal to e to the 0, which is 1. So my p sub n function of x is equal to 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed up to 1 over n factorial x to the n. And so this function's purpose in life is to approximate e to the x near x equals 0. And the more terms you use, the more accurate it will be. Next, let's find the nth Maclaurin polynomial for f of x equals sine x. This one's a little bit trickier to find the nth one because there is some sign switching going on, but we'll discuss that in a moment. So first we need a pattern for the derivatives of sine x. So our function f of x is equal to sine x. The derivative of sine is cosine. The derivative of cosine is negative sine. And the third derivative will be negative cosine x. And then the fourth derivative, the derivative of negative cosine, will bring us back up to sine. So these derivatives are going to cycle in groups of 4. So remember, in general, we have p sub n of x will equal f of 0 plus f prime of 0 times x plus f prime prime of 0 over 2 factorial times x squared plus the third derivative at 0 over 3 factorial x cubed, etc. Nth derivative at 0 over n factorial. So in our specific case, that will be equal to sine of 0 plus cosine of 0 times x minus sine of 0 over 2 factorial times x squared minus cosine of 0 over 3 factorial x cubed, and then plus sine of 0 over 4 factorial x to the 4th plus, etc. So sine of 0 is 0, cosine of 0 is 1, so we have x. So this term is 0, this term is 0, that term is 0. So x minus x cubed over 3 factorial. Next we will have plus x to the 5th over 5 factorial. All of the even parts of this are going to involve having a sine of 0 or negative sine of 0, which are going to 0 out. The next term will be minus x to the 7th over 7 factorial, and then plus x to the 9th over 9 factorial. And it's not clear what to do with the n, so I'm just going to put a minus next and then dot dot dot, because this is the pattern that continues. And one interesting thing you can see here is that you know that sine is an odd function, and it's Maclaurin polynomial. In the Maclaurin polynomial, all of the powers of the x's are odds. Next, let's find a Taylor polynomial, so not centered at 0. This time it's centered at c equals pi thirds. So once again, third Taylor polynomial means we're going to need 3 derivatives. So the original function is sine. The first derivative is cosine. The second derivative is negative sine. And the third derivative is negative cosine. And instead of plugging in 0, now we're going to plug in pi thirds. So f of pi thirds. So sine of pi thirds is root 3 over 2. F prime of pi thirds, that will be cosine of pi thirds, which is 1/2. The second derivative of pi thirds will be negative root 3 over 2. And the third derivative at pi thirds will be negative 1/2. Now the third Taylor polynomial at x is given by f of c plus f prime of c multiplied by x minus c plus the second derivative at c over 2 factorial x minus c squared plus the third derivative at c over 3 factorial x minus c cubed. Thus, p3 of x will equal, so f of pi thirds is root 3 over 2 plus 1/2 multiplied by x minus pi thirds plus root 3 over 2 times 2 factorial, and actually that should be a minus because I was plugging in negative root 3 over 2. Multiplied by x minus pi thirds squared, and then minus 1 over 2 times 3 factorial x minus pi over 3 cubed. So this polynomial would do a good job estimating values of sine near pi thirds. find the Maclaurin polynomials P0, P2, P4, and P6 for f of x equals cosine of x. So P0 of x is equal to just f of 0, and cosine of 0 is 1. Now P2 of x, that will equal f of 0 plus f prime of 0 times x plus f prime prime of 0 over 2 factorial times x squared. So we might as well find some derivatives of cosine. So f of x is cosine. The first derivative of cosine is negative sine. The second derivative will be negative cosine. And plugging in 2, that gives us that P2 of x is equal to, so f of 0 is cosine of 0, which is 1. Then f prime of 0, sine of 0 is 0, so that term will be gone. We'll have 1 minus x squared over 2 factorial. So there's the second degree Taylor polynomial. Next, let's find the fourth degree Maclaurin polynomial. So in this fourth degree polynomial approximation, we will add on the terms with x cubed and x to the fourth. So we can just take the part we did in P2, 1 minus x squared over 2 factorial, and add on the third derivative at 0 over 3 factorial times x to the third, plus the fourth derivative at 0 over 4 factorial multiplied by x to the fourth. So my third derivative will be negative sine, and the fourth derivative will put me back at cosine. And this gives us P4 of x is equal to 1 minus x squared over 2 factorial. Plugging 0 into negative sine yields 0, so the x cubed term is gone, plus x to the fourth over 4 factorial. And by now I think you can see the pattern. In the expansion of cosine, I'm having all of the even powers and the terms are flip-flopping. So just using the pattern, P6 of x will equal 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. And next we're due for a negative term, so minus x to the sixth over 6 factorial. The next term you'd add on for P8 would be x to the 8th over 8 factorial, and then plus x to the 10th, etc. And we're going to use P6 of x to approximate the value of cosine of 0.1. So we'll find P6 of 0.1. That's about equal to 0.995, and that's an estimation of the value of cosine of 0.1. Find the fourth Taylor polynomial of g of x equals ln x centered at c equals 1, and use it to approximate the value of ln of 1.1. So here we're going to do a Taylor polynomial, not a Maclaurin one, so we'll have to use the x minus c's. So your original function is equal to ln x. The first derivative is 1 over x. The second derivative is negative 1 over x squared. The third derivative will be positive 2 over x to the third. And then the fourth derivative will be negative 2 times 3 over x to the fourth. Now in general, P4 of x will equal, in this case, f of 1, because 1 is our c, plus f prime of 1 times x minus 1, plus the second derivative at 1, multiplied by x minus 1 over 2 factorial, x minus 1 squared, plus the third derivative at 1 over 3 factorial, x minus 1 to the third, plus the fourth derivative at 1 over 4 factorial multiplied by x minus 1 to the 4th. So we have that P4 of x. So first of all, f of 1, ln of 1 is 0. Next, f prime of 1 will be 1. So our next term will be x minus 1 plus, now the second derivative at 1 is negative 1, so we'll have plus negative 1/2 times x minus 1 squared plus, now the third derivative at 1, plugging into this, we'll have 2 divided by 3 factorial, which will actually just give us 1/3 times x minus 1 cubed. And then plugging in 1 into the fourth derivative, we'll have 2 times 3 over 4 factorial, and that will just give us 1/4. So our last term will be minus 1/4 x minus 1 to the 4th. So in general, P4 of x is equal to x minus 1 minus 1/2 times x minus 1 squared plus 1/3 x minus 1 to the 3rd minus 1/4 x minus 1 to the 4th. And you can see there's a pretty obvious pattern happening there. So that's the 4th degree Taylor polynomial, and this approximates values of natural log of x near x equals 1. So if we want to estimate ln of 1.1, that'll be about equal to the value of this polynomial at 1.1, which is approximately equal to 0.0953. Anytime you're using an estimation technique, it is very useful to discuss how accurate that estimation technique is. So that's the idea behind the remainder of a Taylor polynomial. So if you have this function f of x and it's equal to the polynomial expansion plus some remainder. So this is your estimate and this is the remainder. And that tells you that the error that you make is then equal to the absolute value of the remainder for some particular x, which is the same thing as taking the difference between the function value and the polynomial value at that particular place. Now the next theorem we're going to discuss gives us a bound on this error. So Taylor's theorem, or the Lagrange form of the remainder, says that your remainder is equal to the value of the n plus first derivative at some z, and that z is between x and c, where x is the value you're estimating and c is where you're centered at. So the remainder is equal to the nth derivative at some z divided by n plus 1 factorial multiplied by x minus c to the n plus first power. So we're not going to ever find this z exactly, but what it does tell us is that the remainder is less than or equal to this expression. So x minus c to the power of n plus 1 over n plus 1 factorial multiplied by the maximum value of the n plus first derivative. And it is possible to use calculus to find the maximum value of that derivative. Often it's the case that we're looking on this little closed interval and the maximum value is at one of the endpoints. But that will give us a bound on the error, so like an absolute worst case scenario. So approximate f of 0.1 using a Maclaurin polynomial of degree n equals 4, where f of x is equal to e to the 3x, and we're going to determine the accuracy of this approximation. So first we have to find the 4th degree Maclaurin polynomial. So first notice that f of x is equal to e to the 3x. The first derivative is equal to 3e to the 3x, which is the chain rule. The second derivative is equal to 3 squared, or 9e to the 3x. The third derivative is equal to 3 cubed e to the 3x. And the fourth derivative is equal to 3 to the 4th times e to the 3x. And then p4 of x, since we have a Maclaurin polynomial, we're centered at 0, that will equal f of 0 plus f prime of 0 times x plus f prime prime of 0 over 2 factorial x squared plus the third derivative at 0 over 3 factorial x cubed plus the fourth derivative at 0 over 4 factorial x to the 4th. Now f of 0 will equal 1. F prime of 0 is 3. F prime prime of 0 is 9. The third derivative at 0 is 27. And the fourth derivative is 81 at 0. Now there is some cancellation that you could do there if you wanted to, but I think this is good enough. And then we are going to estimate f of 0.1, which is the same thing as p of, which we'll estimate using p sub 4 of 0.1. And when you plug that in, you get, this is about equal, actually exactly equal to 1.349835. Now let's determine the accuracy of the approximation by finding an upper bound for the error. So we know that from the previous formula that the remainder of the nth polynomial is less than or equal to x minus c, in this case x minus 0, to the n plus first over n plus 1 factorial multiplied by the maximum of your n plus first derivative. And in this case, because we found R4, we have the absolute value of R4 of x is less than or equal to absolute value of x to the 5th over 5 factorial, and then the max of the 5th derivative. So in our particular case, the x we plugged in was 0.1. So the remainder of the 4th degree Maclaurin polynomial for 0.1 will be less than or equal to 0.1 to the 5th over 5 factorial. And then the maximum of the 5th derivative, so we have to first find the 5th derivative, but that's not super hard. The 5th derivative will be 3 to the 5th e to the 3x. And since we care about, since this remainder is found, the maximum is found on the interval from 0 to 0.1, and e to the 3x is an increasing function, the maximum occurs at 0.01. So the maximum is of the 5th derivative will be given by plugging 0.1 into that 5th derivative. So for the max of f5, we plug in 3 to the 5th e to the 0.3. And working that all out, we end up with an upper bound on the error that is about equal to 0.000027. So that's how accurate this estimate is. The error is less than 0.000027. Next, use Taylor's theorem to obtain an upper bound for the error of this approximation, and then calculate the exact value of the error. So first of all, what we have to notice is that what we have here is p5 of x, so the Maclaurin approximation of e to the x 5th degree, which is 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x to the 3rd plus 1 over 4 factorial x to the 4th plus 1 over 5 factorial x to the 5th. And the number that's been plugged in is 1. So they have found P5 of 1, which is an estimate of e to the 1 power, or e. Now, Taylor's theorem says that the remainder here is less than or equal to your x value to the 6th power over 6 factorial multiplied by the absolute value of the maximum of the 6th derivative. And in this case, our x value was 1, so our remainder is less than or equal to 1 to the 6th, or 1, so 1 over 6 factorial. And because our function was e to the x, and the interval we care about is 0 to 1, because 0 is where we're centered and 1 is the value we plugged in, the maximum value will be e to the 1st, which is about equal to 0.003774. So that's the max error, according to Taylor's theorem. Now, how you'd find the exact, or the actual error, is you take the absolute value of e, so using some kind of calculator, minus this approximation, so minus 1 plus 1 plus 1 half, etc. And when you work that out, it's approximately equal to 0.001615. So as you can see, this should make sense, this first number we found is the maximum possible error, as in the absolute worst case scenario. So the actual error should be less than or equal to that, and it was. So this was about 2 1/1000ths less. On your homework, don't worry about the accuracy thing. On the homework or the quiz, I'll have to specify how many decimal places I want you to use, and the WebAssign does the same thing. And the last example, we are going to determine the degree of a Maclaurin polynomial required for the error in the approximation of cosine of 0.1 to be less than 0.001. So our theorem says that the absolute value of the remainder is less than or equal to x to the n plus 1st power over n plus 1 factorial multiplied by the max of the absolute value of the n plus 1st derivative. Now, because our function is cosine, so our function f of x is equal to cosine x, and the x value we care about is 0.1, we know that this remainder will be less than or equal to 0.1 to the n plus 1st power divided by n plus 1 factorial. And now the maximum of the derivatives, cosine's derivatives fluctuate between plus and minus cosine and plus and minus sine, and the maximum of all those functions is going to be 1, so multiplied by 1. Now, at this point in time, what we do is we just test various values of n, and we look and see and find the first one where the error comes out to be less than 0.001. So when we plug in n equals 1, I get 0.005 for this expression. So that means that the maximum error is 0.005, which is not less than 0.001. When I plug in n equals 2, the error that I get is 0.000167, and this is less than 0.001, so we actually only need to use a polynomial of degree 2 for that approximation's error to be less than 0.001. So when you're doing this on your homework, you're looking for the very first value when this error that you find using this estimate drops below that value.